Hello students, welcome to the 38th lecture on particle physics. And in the last lecture, we were discussing about neutrino oscillation. And let's continue from there. And today we shall talk about two-flavor neutrino oscillation. What I had told you, for example, in the accelerator experiments, protons are bombarded on target material. And then from there, pions are produced, and these pions are then collimated using magnetic field. When they travel, they have got finite lifetime. They give rise to muon and neutrinos, corresponding neutrinos. And then when these neutrinos travel in space, then we can place another detector at some distance. And if we are looking at the disappearance in the signal, then the detector will be sensitive to detect muons. If we are looking for the appearance experiment, then the detector will be sensitive to detect electrons, for example. And today we shall talk about the two-flavor neutrino oscillation. And what I had told you, that neutrino oscillation is purely a quantum mechanical phenomena which happens because the neutrinos, when they travel in space, they travel as a combination of mass eigenstates, and they have the different frequencies, and because of the different frequencies, when they travel in space, they have different phases, and these waves of different phases, when they overlap, they give rise to one flavor of neutrinos. Then when again they propagate and overlap again, they give another type of flavor of neutrinos. And this is how you can have muon type neutrino, electron type neutrino, and electron type neutrinos again giving rise to muon type neutrinos, etc. Therefore, the probability of measuring a particular flavor for a neutrino varies between three known states. That is what we talk about, nu1, nu2, and nu3. If we say that there are three flavor neutrino states, and the oscillation probability, if we consider just only two flavors, this alpha can be an muon type neutrino we are talking about, or we are talking about electron type neutrinos, then this is the oscillation probability of nu mu's transforming to nu e's, and this is sine square 2 theta times sine square this guy. This theta is the maxing angle, and delta m square is the difference in the mass square of the different eigenstates. L is the length through which that neutrino has traveled, and E is the energy of the neutrino. Today we shall try to obtain this result. Now, if the mixing angle is 0, then you can see that there will be no oscillation. And that means even if I ask you the question, what will be nu alpha to nu alpha, that means muon type neutrinos remain as muon type neutrinos, will be 1 minus nu alpha times nu beta. And if this is 0 for theta equal to 0, then that means all the time muon type neutrino will remain as muon type neutrino. Or if delta m square is 0, then also the oscillation probability of transforming nu alpha to nu beta, that will be 0. And that is why when I was talking about the difference in the neutrino mass eigenstate, then at least one of them should be non-zero. That is when you will have a finite delta m square. Therefore, it is not necessary that both of them are non-zero. At least one of them has to be non-zero to have a finite delta m square. And if we are saying that theta equal to 0, then that means neutrino mass eigenstates are the same as neutrino flavor states, and that is why there is no oscillation. If there are two flavors, there will be two mass eigenstates. This parameter is the difference, delta m square is the difference in square masses of each of these states, delta m square that we are talking about, this is m1 square minus m2 square or m2 square minus m1 square, depending upon how you define it. For neutrino oscillation to occur, at least one of them should be non-zero. Now let us try to obtain this result. For example, what I had told you, that we are starting from a nu mu beam, and then we want to see how many of nu mu's have got transformed to nu e, or you can say that as nu mu propagates in space, how many nu mu's remain as nu mu's. Therefore, what we are talking about, nu mu and nu e as the flavor states, and then we have a unitary mixing matrix, cos theta sin theta minus sin theta cos theta, and here this is nu1 and nu2. This is what we have, and as you can notice that this theta is the mixing angle. That means if we talk about nu mu, this will be cos theta nu1 plus sin theta nu2, and nu e will be minus sin theta nu1 plus cos theta nu2. This is an important aspect, and the important point is that when we are talking about nu mu and nu e written in terms of nu1 and nu2, these nu1 and nu2 are the mass eigenstates. Therefore, this nu1 and nu2 evolves in time, and that is why we, in using quantum mechanics, as neutrino oscillation is purely a quantum mechanical phenomena, this nu1 to t, we can write it as nu1 at time t equal to 0 e power minus I e1t. I am using the units of h cross c is equal to 1. Then I will write one expression when I will be specific to the proper units, and there we will see that how the formula for the oscillation probability looks like. And similarly, nu2 t is nu2 t equal to 0 e power minus I e2t. Now, what is E1? This is square root P square plus M1 square. E2 is square root P square plus M2 square. This we have to keep in mind. And we know that neutrinos are relativistic particles. Therefore, this we can write it as just P square 1 plus M1 square by P1 square, and this will be equal to then P outside 1 plus M1 square upon twice P square, and that means this is P plus M1 square upon twice P. Therefore, similarly, E2 will be P plus M2 square by twice P. And then when I will talk about E2 minus E1, these are the different momentum states. The difference in energy is because of the difference in the masses of these two eigenstates, which are the propagation states. Therefore, what we will see that when we will talk about E2 minus E1, for example, then this will be M2 square by twice P minus M1 square by twice P, and this will be nothing but M2 square minus M1 square upon twice P. And this M2 square minus M1 square, we will call them by delta M square. Therefore, important point is that we are writing nu1 t as nu1 t equal to 0 e power minus I e1 t. This is the quantum mechanical evolution equation that we talk about. Now, this is nu mu and nu e written in terms of nu 1 and nu 2. At the same time, using inverse transformation, you can write nu 1 and nu 2 in terms of nu 1 and nu 2 in terms of nu mu and nu e. And how that would look like, that will be simply nu 1 nu 2 inverse transformation. This will be equal to cos theta minus sin theta cos theta nu mu nu e. Therefore, what we are doing, here we had started with this transformation matrix, and then we are here writing the inverse transformation matrix. Why I have written this equation? This is because suppose we start with a pure muon neutrino beam, and then that pure muon neutrino beam is propagating in space as a mixture of nu 1 and nu 2. Now, when we are talking about mixture of nu 1 and nu 2, because they have got different frequencies, they develop different phases, and this is what we are talking about, that as these neutrinos travel, because of the different phases, then overlap. Somewhere you will have simply the production of nu e, at some other place you will have the production of nu mu, and therefore this is what we are talking about, transformation from nu mu to nu e and then back to nu mu. Or we say that when we have nu mu as a beam, as the blue line represents the point from where you are producing muon type neutrinos, at this point all that neutrinos that you have is muon type, and electron type neutrino is 0. But as it propagates, as you can see, because of the previous figure, you can directly see that you have here the muon type is minimum and nu e is maximum, and then nu mu is maximum and nu e is minimum, and so on. And that means with oscillation length you have the chances of nu mu and nu e, those are changing. And that is why when the experiments that is designed, that is also sensitive to this oscillation length and the neutrino energy that with which we want to perform the experiments. For example, if I talk about T2K experiment, then the T2K experiment has the average neutrino energy of 600 MeV, while the NOVA experiment that is being performed at Fermilab, the average energy of the neutrino is 2 GeV. The Dune planned experiment at Fermilab, that will have an average energy of 2.5 GeV. Therefore, the important point is the energy of the neutrinos, those are varying, the average energy. Similarly, accordingly, we have to see the oscillation length to look at the either muon appearance signal or to look for the muon disappearance signal. That is why we are talking about these concepts. And the important point is that when I am telling you that my experiment is going to start at time t is equal to 0, then at that time whatever nu mu that you have is muon type. There is nothing else. Therefore, nu mu at time t equal to 0 is 1, and nu e at that point of time is 0. Nu mu at time t equal to 0 is 1, and at that point of time nu e is 0. This is an important concept which has to be kept in mind while talking about neutrino oscillation. And then what we did, we wrote nu 1 nu 2 as equal to cos theta minus sin theta cos theta nu mu, nu e. Therefore, you can say that nu1 is nu mu cosine theta minus sine theta nu e, and nu2 is nu mu sine theta plus cosine theta nu e. Now we will talk about the time t equal to 0. Now when I will talk about time t equal to 0, then at that point this guy will not be there and this fellow will also not be there. Therefore, at time t equal to 0, nu1 at time t equal to 0, this will be nu mu t equal to 0, and with this you have cosine theta, and nu2 at time t equal to 0 is nothing but nu mu 0 sine theta. Therefore, this we have to keep in mind when we are talking about neutrino oscillation. Now, what we are talking about? We are talking about how many nu mu's have got oscillated. That means we want to measure the intensity of the nu mu's after a time t upon the intensity at time t equal to 0. Therefore, the oscillation probability that we want to talk about is I mu t upon I mu time t equal to 0. And when we are talking about intensity, then that means this will be nothing but amplitude times the roughly the conjugate of the amplitude of mu, nu mu and nu mu star. What is the amplitude? The amplitude is simply nu mu t upon nu mu at time t equal to 0. What is my nu mu t? Recall from the earlier expression of this matrix. This was sine theta minus sine theta cosine theta nu1 nu2. Therefore, nu mu is cos theta nu1 plus nu2 sine theta. Therefore, this will be what? Cos theta nu1 t plus sine theta nu2 t upon nu mu. Let us just, instead of writing all the time equal to 0, this we are writing as nu mu 0. Now, what is nu1 t? This is nu1 0 e to power minus I e1 t. Therefore, in my next step, I am writing it as cos theta nu1 0 e to power minus I e1 t plus sine theta nu2 0 e to the power minus I e2 t upon nu mu 0. And you can see that what is nu1 0? This is nu mu 0 cosine theta. And what is nu2 0? This is nu mu 0 sine theta. Therefore, if I replace nu1 0, we will have nu mu 0 cosine theta. Therefore, this guy will become in the numerator the first term cosine squared theta nu mu 0 e to power minus I e1 t, and the second term will become plus sine squared theta nu mu 0 e to power minus I e2 t. Therefore, try to look at it the term which I am talking about. Look at it carefully. What is this a mu? Our a mu is cos theta times nu mu 0 cos theta. That means cos squared theta from minus I e1 t plus sine squared theta e to the power minus I e2 t. This will be a mu. What will be then this a mu star? Simply we will replace minus I by plus I, and therefore what will be the a mu star? A mu star will be equal to cos squared theta for minus I e1 t plus sine squared theta e to the power minus I e2t times cosine square theta e to the power plus I e1t plus sine square theta e to the power plus I e2t. And then you can notice that there will be four terms. The first term will be cos 4 theta because minus I e1t and e to the power plus I1t will cancel out. Then you will have one term cos square theta sine square theta e to the power I e2t, then sine square theta cos square theta e to the power minus I e2t times e to the power I e1t, and then plus sine 4 theta. These two terms will then cancel out. Therefore, one term will be cos 4 theta, the other term will be sine 4 theta, the third term will be cos square theta sine square theta e to the power I e2t times e to the power minus I e1t. So, therefore, let us write them. What is your mu star? This is cos 4 theta plus sine 4 theta plus sine square theta cos square theta e to the power I e2t times e to the power minus I e1t plus sine square theta cos square theta from minus I e2t times e to the power I e1t. This is what we will have. As you can see, cos 4 theta cos square theta times sine square theta e to the power I e2t times e to the power minus I e1t plus sine square theta cos square theta power minus I e2t times e to the power plus I e1t plus this is sine 4 theta. Therefore, what you have these four terms. This we can write it as cos 4 theta plus sine 4 theta plus, let us take this common, sine square theta cos square theta e to the power I e2 minus e1t plus or minus I e2 minus e1t. That is all. Now you notice this is something like power I theta plus e to the power minus I theta. Therefore, what we are going to do, we are going to write it as cos 4 theta plus sine 4 theta plus, first let us write it this, 2 sine square theta cos square theta e to the power I, remember e2 minus e1, this will be m2 square by twice p minus m1 square upon twice p times t. Okay, let us for time being, let us stick with e to the power minus e2 minus e1t plus e to the power minus I e2 minus e1t by 2, and then we add 2 sine square theta cos square theta here and subtract the same. Therefore, this will become cos 4 theta plus sine 4 theta plus 2 sine square theta cosine square theta minus 2 sine square theta cosine square theta plus 2 sine square theta cosine square theta, this factor. Now notice this is nothing but sine square theta plus cosine square theta whole square. Therefore, what you have is sine square theta plus cosine square theta whole square minus 2 sine square theta cosine square theta 1 minus cos e2 minus e1 t, and this we can write it as 2 sine square theta by 2. Therefore, this will become, this is sine square theta plus cosine square theta is 1, and notice here this is, if I am writing it as 2 sine square E2 minus E1 times t. This 2 with this 2 will become 4, and then we have 4 sine squared theta cosine squared theta, and this 4 sine squared theta cosine squared theta we can write it as 2 sine theta cosine theta whole square, and that will be equal to sine 2 theta whole square, and that will be equal to sine square 2 theta. Therefore, what we have, 1 minus sine square 2 theta times sine square E2 minus E1 times t by 2. This is the ratio of the intensity after a time t to the intensity at time t equal to 0. Okay, we shall stop here and we shall start from this point to see how this E2 minus E1, when written in terms of delta m square and the length, because we are talking about the time and neutrinos travel with a speed of light. Therefore, as we know that the distance speed is distance upon time, therefore this will be L by t, and this will thus give us t is equal to L by c. Therefore, we will replace this t by the oscillation length, and then we will obtain the expression for the oscillation probability. Let us stop here. See you in the next class. Thank you very much.